If you're a musician, you're going to want to know what these shapes are, and there's a chance that they're about to become your new favorite mathematical curiosity. They're called Lissajous curves, and they were discovered by French physicist Jules-Antoine Lissajous using his famous tuning fork experiment. Let me show you how it works. The experiment involves two tuning forks with two small mirrors glued to their tines. A laser is bounced off each mirror and onto a screen, so that the vibration of one tuning fork makes the laser point move up and down, and the other makes it move left to right. But when Lissajous struck both tuning forks at the same time, he found that the point traced out a circle. And when he swapped out one of the tuning forks for one that vibrated at twice the frequency, the laser traced out a figure 8. Lissajous experimented with pairing different tuning forks that vibrated at different frequencies and found that the shape created was dependent only on the musical interval between the two tuning forks. For example, this particular pairing of musical notes is called a major third, and when these tuning forks are used in the experiment, they create this shape. With this experiment, Lissajous discovered a unique shape corresponding to every musical interval. What I find fascinating about this chart is that some element of the character of each interval seems to come through in these visualizations. Nicer sounding intervals produce simpler shapes, and more dissonant intervals produce squigglier shapes. Pretty interesting. But can we take this idea even further? Okay, so a Lissajous curve is a visualization of a two-note interval. But most of the time, music isn't about just two notes. Musicians often base their music around chords of 3 notes or more. But in order to create a 3-note Lissajous curve, we're going to need to step into the third dimension. So instead of just having our laser point wiggle left to right and up and down, it's going to have to wiggle forward and backward too. Let's tie the x, y, and z coordinates of this point to 3 oscillators on the x, y, and z axes. As they move, the point should trace out a 3D Lissajous curve in space. We'll start by plugging in the frequencies of the major triad, which is probably the most common type of 3-note chord in modern music. Now that we have this 3D shape, we can 3D print it. Nice. Let's do the same thing for the minor triad, which is probably the second most common chord. I like how if you look at it down any axis, you can see the 2D Lissajous curve representing the constituent intervals that make up this chord. Thanks for watching.